Okay, so based on the last talk, we were trying to kind of like build an anonymous broadcast system at Flashbots, and like here, this is very much work in progress, as the slide says, and it will say it again at some point when it gets even more questionable. So like I'll present like some of the main ideas of like, how we, for example, kind of like follow previous designs, how we differ from previous designs. And then hopefully this will be leading to an engaging discussion later on in the breakout sessions about like, what are the best trade-offs to take for building an efficient anonymous broadcast system. And we kind of like the main starting point of this work is really kind of like the very nice observation from the ZipNet paper that really says that like, you can use TEs in a kind of like clever way where you say, okay, like privacy holds in the classical cryptographic non-collusion assumption. You assume a lot of parties may be malicious, but at least one party is honest, and like privacy is based on that. And the TEs kind of allow you to avoid doing a lot of kind of like expensive extra work that kind of like maintain liveness. So if the TE fails, then it fails loudly and kind of the protocol breaks down and you can see that something went wrong. So it's like a falsifiable assumption. So that's a very nice observation made in the ZipNet paper, which we kind of like also try to exploit here. And kind of like for this talk, we'll also follow roughly the setting of how ZipNet does it in the set. Oh, this will be in. Sorry. Wait, I have to go into full screen mode. Okay, yeah. So we will be following kind of like the rough structure of how ZipNet views the problem. So we will have the clients. Each client has a message. We will have some aggregators, which will basically be parties that are not trusted. So they will just kind of like take some computational work off the servers, which will then be in charge of publishing the messages. So like you assume among the servers, at least one is honest, in the ZipNet paper at least, and the aggregators, like nobody needs to be honest, and the clients want to send their messages. And you want anonymity, so like at the end, message M1 should be published, and like you should not know which of the clients it comes from. And kind of like the particular focus for like us is really to try to design something that has very low latency so that we can use it in kind of like a block building context. So there's many different designs with different trade-off spaces. So what we try to really optimize, like the ZipNet paper, is to say, okay, we want to have the smallest possible latency and a somewhat simple protocol design that is like easy to implement and like really works as fast as possible in practice. Okay, so just to recall again, so these aggregators are completely untrusted. They're like, even if all of them are corrupt, privacy doesn't break. And one difference compared to the ZipNet paper is that the ZipNet paper says like all but one parties can be corrupt, which is nice from a privacy perspective, and but is can be more problematic from a liveness perspective, because that means that if one of the servers goes offline, then your messages stop arriving. And the ZipNet paper mentions like in one sentence that you can extend it, but I think there are some like technical difficulties of how to extend it, and like we try to build something where you have kind of like this liveness safety trade-off in a more straightforward fashion. So this is like kind of like a different point in the design space, and then it's debatable which one is better. Okay. Yeah, so what we want is we want liveness, the messages arrive, and we want security, that the messages cannot be linked to the clients. So kind of like one of the goals, as I said, is that kind of for us, it could like, if we repeatedly use the system, sometimes one of the servers might be slightly slower in responding. So we kind of like don't want to completely abandon it, and we want our messages to still arrive if some of the servers are like offline for a few rounds, for example. And in comparison to like how at least I see how I would extend ZipNet is that we don't need any kind of distributed key generation among the servers, and we don't need any kind of distributed PRFs, which if you don't know what it is, it's like, it's not the worst tool to use in terms of computational complexity and like general complexity, but like it's nice if you can avoid it, so we try to avoid it. On the downside, well, or like the trade-off space is that we say the ZipNet paper scale is really great if you have a lot of servers. So if you have 1,000 servers, then the ZipNet kind of like construction still works well. if you were to put like 10,000 servers in our construction would not work well at all. But like we assume that we don't have too many servers. So we have like some number of servers, but like not 1,000. So then kind of like we're okay with the bandwidth slightly increasing with the number of servers. We show that you can actually fully avoid the slot reservation stuff. So like it was shortly kind of like touched upon that you need to reserve a slot and then kind of like put your message there. In our kind of work, we show that you just don't need to do any of that. You just kind of like, if you put your message in specific slots in the right way, then you can kind of like bypass this whole shenanigans. And the last thing is that like, let's see how much time we will have, but like in the ZipNet design, the messages from the clients to the aggregators are authenticated, but the messages that the aggregators produce to send to the servers are kind of like, they're authenticated as originating from some aggregator, but they're not authenticated as in the sense of like that the computation that they did is correct. So like they can send you garbage and you don't have a easy way of distinguishing whether you get good messages or bad messages from the aggregators, which can potentially be an issue. So we show that like you can get rid of this attack vector and you can just have like a somewhat lightweight process of arguing that aggregators' messages are well formed. Okay, yeah, this is work in progress. I thought it would be easier than it was. I have a construction, but if you have a better one, then you're welcome to suggest it. Okay, so the starting point of this is like the most basic, if you want to do any kind of like secure computation in a distributed network, the most basic protocol that you can think of is secure addition. So what is secure addition? Well, assume you have 3 messages and you don't want to broadcast anything. You just want to add them securely. Okay, so like you want that the 3 parties start with their individual messages and at the end they learn the sum of the messages. And kind of like how like these classical protocols work is they do the following. Basically, each client can split their message into 3 chunks. And then they basically send one of their chunks to server 1, one of their chunks to server 2, and one of their chunks to server 3. Now the servers each have 1 chunk of each message. If you corrupt any 2 servers here in this case, you learn nothing about the messages because kind of you need 3 chunks to reconstruct the message. The servers can sum up the chunks that they have and reveal them. And if you sum up those sums, then you just get the sum of the messages. And you can argue that any kind of corrupt server any corrupt server or any 2 corrupt servers learn nothing other than the output of the messages that they see in the network protocol. Okay, so why is this useful? Yeah, that's what I said. So yeah, and now in this protocol, I said that if the servers only see 2 of the kind of like shares out of 3, then they learn nothing, but you can make it a trade-off. So like there's easy extensions of how you say that, like, you know, if some servers are offline, like this is with 3, but you can have it with n servers. You can say if some servers are offline, then like it still works, but like then you get a slightly lower privacy threshold in terms of how many servers can be corrupt. So like this is a straightforward thing that I'm kind of ignoring how exactly you do it. You basically replace the sum by polynomials on a very high level. Okay, so then the simple blueprint of how you now try to build an anonymous communication system out of it is the following. You say, as in the ZipNet paper, you say, okay, I will take my message and I will look at a large array of data blocks and I will just put my message in a random location. And now what I do is, well, I kind of like use the protocol that I described before, which works for like scalars. I just use it on vectors now, which is kind of the same thing, just many times. And I compute the sum. And if everything went well, then the messages all land in like individual slots and we all learn kind of like the different messages. But because the message locations in the array are chosen randomly, they have no connection to who actually sent the message. So you kind of like get an anonymous broadcast immediately. Now the problem is, and this is why you usually kind of like use slot reservation, is because if you put messages randomly, then unless you make your array extremely big, you will have collisions. So, you know, if you have a collision, you get like the sum of messages, like how do you recover the message that you actually wanted to send? And the idea is kind of simple. So what you do is, in addition to like, so here you have an example where you put 3 messages in this array and 2 of them collided. Well, imagine you just also did it a second time with a smaller array. You took your 3 messages and also put them in a smaller array. And both times you had some collisions. But the nice thing is that now in the top one, you can extract the first message. And magically, if you can extract it from the first array, You also know where it is in the second array, so you can remove it from the second array. And now all of the sudden, kind of like the collision in the second array went away, and you can extract all the messages. So this is like a very, very toy example of like a technique that is called invertible Bloom filters and or invertible lookup tables. And then there's an improvement of this data structure called stacked invertible Bloom filters from last year, which effectively says that like the amount of slots that these arrays have to have compared to the amount of data that you send is very good. So if you have n messages, then the number of slots that you need to have for this kind of procedure to work is less than twice the number of slots that you need for just sending the messages without anonymity. So using this approach, you just put your messages in somewhat random places, and you can extract them without needing to do any sort of slot reservation. So these are the first two things on a high level, at least. Now, the last thing is that, like, what I shortly mentioned is that, like, you have this aggregator, and let's say you have one aggregator here. The client split their message in, like, chunks of messages, and, like, the details are not important, but, like, what is important is that, like, some of those chunks go to a server here. Well, yeah, so a server, and the server wants to compute the sum of those messages, which is, like, this output in the secure addition protocol. Now, kind of like you don't send stuff in plain over the network. You have some agreed key material. So like in addition, like these messages are plus some key, which like I'll show here for completeness that they're not sending them in plain, but like you have privacy, but it's not so important what they do. So now in this like ZipNet design is that these messages would go to the aggregator, and the aggregator sends something to the server, and the server then reveals something. And the aggregator would ideally like to compute the sum of those messages that is encrypted in the sense that like it is like still contains this K12, K22, K32 random pads, which you can think of as keys. And now it is sent to the server, and the server strips those pads and reveals the message, which kind of would complete the protocol. Now, even if you authenticate the messages from the clients to the aggregator, the message from the aggregator to the server is not authenticated. And the reason is that it's a little bit tricky to authenticate it, actually, because like you're changing the message, like you're adding a bunch of messages together. So if you signed the original messages, now you don't kind of like, you cannot verify the signature anymore because you have the sum of the signatures, or like the same with a message authentication code. But what we effectively show is that you can construct such a object in a kind of lightweight fashion, which allows you to do the following. So if you have like client I has key I, and the server has all the keys, and each client authenticates their message with like some tag tau, then the aggregator can just compute the sum of the messages and compute a tag that authenticates the sum of the messages under independent keys. And now the advantage is that like when the server receives messages from the aggregators, they can actually verify that this is a well-formed message and not just garbage, which we think is a nice thing. Yep, this was pretty quick, but like hopefully clear enough to motivate some discussions. Yeah.
Yeah. Well, in the interest of time, we're gonna go into a couple quick, just tying things together comments. We also get to extend the clock. Sometimes if you tip enough, it works. Know your tip. But that said, I wanted to kind of make sure that, you know, there's a lot of, like, people will be asking, okay, why the hell is Splashbox working on a MixNet again, right? If you're lost with that question, so I did prompt Phil to just kind of give a very quick kind of a direct answer, what, I guess, technical challenge we're trying to solve and why this path.
Thank you, Tina, for the totally not planned in advance question. So yeah, there's many places I think we can use anonymous broadcast in MEV. One is like the mempool transaction submission gossip layer. We've heard about that already. So even if you're running, let's say, a piece of infrastructure, how do you know that someone's not stopping certain requests or packets from reaching you? That's a super suppression problem in crypto. Another interesting one is like there's this idea that if you have privacy, you're just able to speak more freely. And when you look at infrastructure participants like stakers and block builders and people like this that are speaking over these very police channels, it's very hard to imagine that even if you kind of compel them with things like inclusion lists to be censorship resistant, that the fact that they're doing this all in the clear would like stand up to scrutiny. So privacy also helps a lot there.
Thanks for bringing us back down to earth. I see Tomasz there. You just walked in. Yes. Well, we just started, by the way, just so I hope that you get enough caffeine or drinks outside. And also just like one quick comment and question on the DCNets, ZipNets author, because I think a fan did not realize we were actually, playing around and, exploring implementation of it. So what was your kind of response in terms our like design and kind of like any thoughts and questions?
I think there's a lot of good ideas. Very nice. I definitely want to follow up tomorrow with a clear mind and jet lag right now. But we also, I think, thought of some of the designs and decided to not do that for performance reasons. I also want to, I guess we can talk about that as well. But I think these are interesting improvements. Definitely want to learn more.
Thanks.